plug in your user stuff. And basically what I want you to do is, I mean, there's lots of ways you can do this, right? So basically what I want you to do is like, so I'll help you get started with it, but basically just like, for example, I don't know, example um, 1.12, just literally scribe it, right? Just solve, and then you have some commands for you can do for like math mode or whatever. X1 minus x3 or x3 x2 plus x3 equals 1. And then if you compile it, and this thing has a compiler, so you can see right here that it produces everything you just wrote, right? So basically, I assign you a question. I want you to just scribe it basically on LaTeX. And like I said, I mean, it looks like coding kind of, but it's really not. I mean, there's like maybe like a few things you have to know, but I can help you with that. And even if you like don't ask for my help, you can just like in all programming languages, just Google, right? You Google what does this do? How do you do this? You can just do that, right? So again, this is LaTeX. So I'll assign you a problem. You scribe it with the solution, and at the end, my hope is basically to put everybody's all the examples I've done, um, put them on one PDF and like upload it on my website once I get that up. But yeah, so I mean, this is one way to do it. Hold on. Oh yeah, I'm just demonstrating LaTeX. So this is one way to do it. I mean, like I said, these are literally way. This is how research papers are done. If you like see something like this, uh, if you ever like go on Google Scholar, it's literally written in this format. Like this is why we do this. This is literally a standard. The other way is to install it basically. So let's say you go to LaTeX projects. Uh, so this one you have it just on your computer. If you go here, you can install the LaTeX as follows. So hold on, maybe I should just. Uh, yeah. I mean, we solved the examples in class, but you can type. You want to type the examples and solve and put the solution in there. But anyway, so what was I doing? Oh yeah, so go here. Let's see. Okay, not that. Hold on. So download Matrix. So okay, so I wanted to yeah, there we go. So just put a LaTeX project download. So basically, this is for every single operating system. So you have Linux. This is where you download for Linux. Mac, you use MacTeX. Windows, you use Mic Pro or TextLive. And once you download this, you want to download a compiler. So one good one is Tech uh, Studio. Tech Studio is a compiler. I mean, you could also do it from your terminal, from Bash or something like that. But this is just for a graphic user interface. But so basically, once you have those two things, you have it on your computer, and it's all just stored in your hard drive. And this one is stored in the cloud, obviously. But either one, you can choose which either one. It doesn't matter. Okay, so let's stop doing that for a second. So any questions on this before? Yeah. Yeah. So basically, once you, I don't know, like for example, let's say you finish this. What I want is basically, I guess, do this. So go on Notepad or whatever you have. Just copy this code right here onto that Notepad, and just send me that Notepad. Okay. This information, because this is what I'm going to use to compile it in my own thing. Okay. Any other questions? I know I saw some. Yeah. Yeah. You should have gotten an email about it already. It maybe, I don't know if it was in spammer, but I also sent out another email where you can just look. I put the key in there. You can just go on Packpack, put that key in, and you can find the art class. But if you need help, you can just email me and I can get you on that. Yeah. His attendance required in class. They make me require it. However, as long as you don't tell, I won't tell. Yeah, I won't make it required, but I mean, obviously you'll be missing the stuff because it's not recorded. So it's, I guess, just miss on your own. I guess I forgot the saying, but like, uh, yeah. So you won't have this like recording at all. Yeah, it depends on you. Yeah, that is just stupidity from us. So like,
Excuse me,
I don't.
Professor.
Uh-huh.
Oh, I joined this Zoom link late, and I didn't see how like you got to all the latex stuff.
Okay, well that's fine. You can just email me and I can just show you through Zoom, office hours or whenever you want. I can help you with it.
Okay, all right, thank you.
The problems are in the notes I give you. So if I assign you example 1.1.2, or during the notes I send you the PDF on Remind. Okay. Okay. So now that we have that, let's uh, let's make iPad. iPad. There it is. Let's view the post and let's screen share. Start broadcast. Okay, so there it is. Almost lost this Apple Pencil. I want to do that. Yeah. Yeah. Like I said, if you signed up for the LaTeX thing, I'll send you once I do because I'm going in order with everybody who signed up first and all that stuff. So once we do enough problems, I'll basically email you or remind you, and all the instructions that you need to do for the LaTeX opportunity. The pack one, I still have to like figure out how to like post it, but that one is I'm basically gonna put these challenge questions, the ones we've been doing here, on there, and if you participate in like solving within y'all's group the challenge question, I also give you credit from that. So I just basically that's the whole point is that I want you guys to be talking to each other. Yeah, that'll be the extra credit. So I'll put once I post that all the challenge questions, just go on there. I don't know, give your whatever. Is there an SI session for this course? I actually don't know. I wasn't assigned an ETA, so I'm not sure. Um, there are tutoring things you can do, but other than that, the tutoring stuff is on the syllabus. If you saw all the stuff in there. Other than that, I don't. Yeah, I don't think I got assigned a TA. So unfortunately, I'm only a graduate student, so I don't get one. Okay. So last time we talked about. Oh yeah. So basically RREF, right? We solved a bunch of systems of equations with that, and at the end, I just gave you that challenge question. So, but that pretty much covers all of that chapter that we need to do: is how to solve the systems of equations, how to analyze when the system has no solution, a unique solution, and infinite solutions, right? And I showed you all the forms that you can have for that. So that's pretty much chapter one in a nutshell. And for this next one, we'll be starting chapter two. So chapter two, and this would be matrices. So we talked. I mean, we've messed around with matrices a little bit in this chapter one stuff. However, now we're gonna actually formally like start talking about what how matrices work. All the nitty gritty of all that stuff. So first section to 2.1, which is titled Operations with Matrices. Okay, so basically we're just going to formally define what it means to multiply matrices, what it means to add matrices, and also what it means to have linear combinations and use these to, again, express things like systems of equations. So first definition is this. Let A and B be n by n matrices with real value entries. Then, let's see. Check here so I can see. Okay. Then we say, so first, what does it mean for two matrices to be equal? So we say that A equals B if each so each entry in my matrix has to be equal. So for all I, so this is a, so for all I, all right, so this is the important part, right? So in order to compare matrices and see if they're equal, we have to be sure they have the same dimensions, meaning they have the same number of rows and columns, right? Otherwise, there's no notion of equal between a matrix, right? So you have to make sure that these two things are, before you start like equating the little entries, you have to be sure that, you know, they have the same size. You can't just start doing it with any matrix, okay? Right, so let's see. Okay, so now we have a notion of what it means for two matrices to be the same. So next, we will, okay, oh yeah, I forgot that. Oh, wait. We will give a informal definition of a vector, okay? So now we're going to start translating all the language that we did with systems equations to languages of vectors. So we can say this, denote or okay, maybe this is better. So a vector, we can say, is a y 1 by n or n by 1 matrix, in which case we'll call a column vector a row vector, and is denoted as this. So usually in the book they bold, if they give you a vector v, they bold it. But since I'm not, I'm not a typewriter, we humans write it as with an arrow over the head, right? So we denote it this way. So the x, so we have x1, x2, all the way to xn. So this is the n by 1. And see, and then we could also denote it. There's also another one we can denote as x1, x2, all the way to, let me put this, well, all the way to xn. Okay, so we denote vectors this way. Okay, so now you can ask, okay, so how does this relate to the vectors I already know? Well, in physics, you have, let's say you have a vector in like the plane. You have an x component and a y component, right? Well, same thing for this one, right? So, like say if you're doing, I don't know, force, like going like, I don't know, this way or whatever, usually the vector would be denoted with the x component like this and the y component like this. So we're messing not just with vectors in 2 dimensions, we're now messing with vectors in n dimensions, okay? So this is what that means, this one here. So it has m components, m dimensions, so yeah, so we can say that this is, so these are m and n dimensional vectors, respectively. Okay, so that's a little bit. So let's see. So the one that that's like from that looks like a column is called a column vector. So I'll denote it here. So this one right here. So let me just copy this. So this one right here, we will call a column vector. And this one right here, we say it's a row vector. Okay, and you'll see why we have this these names, and it's literally coming up right now. So for, let's say, a matrix that is, let's say, an n by n matrix with real entries, right? We can partition this matrix into both row and column vectors. The matrix, oops, into row and or column vectors. And how you do that? Well, if you have a equals, let's say, a11 all the way to a1n, and this goes all the way to am1, and this goes to amn, like this. So basically, you can do it one of two things. You can like literally call each one of these a column vector and write the matrix this way. So let's call all those, like, say, A. So this will be A1 as a vector, A2 as a vector, all the way to a like this, right? So we can represent this matrix as a partition of column vectors, where each of those vectors has components A11 and all that stuff. So okay, so is everybody good with like what each of these mean? Yeah. So I mean, all of these just have. So this one has that one. Obviously, all the entries are just all those entries that you see there. Okay. It's and oh, by the way, so there is a good reason we are doing this. It isn't just like what just happened. It isn't just like useless notation. It's not like someone who just like said, "Oh, let's just do this." Yeah. So now the second way we can partition it is by rows. Instead of doing columns, we can go the other way. So we can go this way instead. Okay. So if you do this and let's call each one of those B, you can do, I don't know, B1 all the way to BM. So those will be row vectors. So you partition it either by columns or rows, like this. Okay. Okay. So now that I talk about this, let's put it to use for a bit. So next, we have to have a notion of multiplying matrices, right? So we just talked about, adding matrices, and also by multiplying by scalars. All right, so the next thing should be the definition. So let's say we have like A, B, the n by n matrices. And let's take some scalar alpha and r. Okay. Oh, and by scalar in this context means a real number. Usually that means you get it from a field, but we won't go into that. So then the sum of A and B is exactly what you would think, right? Is denoted as A plus B is defined like this. So you take A plus B, right? And you literally just add component wise, right? Every little, all the entries, you just add them individually. So like A11 plus B11 all the way to A1n plus B1n all the way to AN1 plus BN1 all the way to so B or A, whatever, real numbers mute anyway, so like this, okay? So just a key remark. You can't just go and add any matrix you want together. There's a special restriction we post on this definition, right? And that restriction is that both matrices have to have the same dimension. Exactly, right? Otherwise, if they don't have the same number of rows and columns, then you can't add them. There's no notion, right? I mean, you could come up with one, but whether that's a well-defined definition or not is, I guess you can just see if it is well-defined. But yeah, so if they're not the same size, the sum doesn't exist, okay? So scalar, and then also we have scalar multiplication. Right? Is defined as, let's say, so say I want to take the alpha and then multiply by my matrix A. Well, that amounts to literally just multiplying every entry by alpha, right? All the way to alpha A1n, alpha A n. Okay. Yeah, so this is how we define it, right? So it isn't just like, it is what it is. We define it this way. Okay. So, okay, so now we have a notion of adding, multiplying by scalars, and when two matrices are equal, right? So now let's put up a result, okay? So this might be an obvious theorem, but proving it might not be so obvious. So let's say this is theorem 2.1.1. So let A, B be n by n real matrices. Oh yeah, and alpha and beta be real numbers. Okay. Then yes, we have these properties. We have that A plus B is equal to B plus A. So the matrices commute. We also have that let's see, one, two. We also have that we also have associativity plus C is equal to A plus B plus B plus C. And then we also have that any matrix plus the zero matrix is the same, right? Let's make this small. Let's see, the other one is alpha times a plus b. Scalars distribute. So alpha a plus alpha b. Also, it's linear in the sense that if we multiply by a plus b, we get this. And then last but not least, you can associate scalars as well. Okay, so we have all these properties, and it isn't just a thing that it might be super obvious, but actually proving it is a different matter. So again, remark um, for the sum to exist, the matrices have to be the same size. Same size. Otherwise, they don't. Okay. So let's look at an example. Let's say this is. So let's say A, B, 4, 0, 5, negative 1, 3, 2, B, B 1, 1, 1, 3, 5, 7, C, B, 2, minus 3, 0, 1. Okay. Okay, so find A plus B and A plus C. So solution, so first, what is A plus B? Well, A plus B. So first check, do they have the same size? Yes, right? A and B have the same, A is a 2 by 3 and B is a 2 by 3, so you can add them. So it will just amount to be 4, 0, 5, minus 1, 3, 2, plus 1, 1, 1, 3, 5, let's see, 7. Size, this will equal, just add them together, like component-wise, 9, right? Okay, what about A plus C? Would that exist or no? No, right? They don't have the same size. A plus C does not exist because they don't have the same size. All right. All right, so now that we talked about, I guess, some of the more easier things, let's talk about what it means to multiply matrices and then how we can relate that to systems of equations. Okay. Oh, I have my phone. Okay. So next, let's define what it means to multiply matrices. So let's say we let A be a, let's say, an n by n by n, and let's say B is a uh, n by p matrix. Okay. Then the product of A and the problem and solution. You have to write. So yeah, but make it clear. Don't just like, yeah. So So it is defined as this. So this is how we define it. So we take A times B, right? So how can we multiply this notion of matrices? Well, first thing we can do is we partition B into row vectors, okay? So we can take A and then take B as as column vectors like this. So it has how many? It has B entries or P. And what you do is, in a sense, you distribute into each one. So this is the first way we define it: is we take each one and multiply it by this. Yep. Okay. So that's one way. And each one of those, you literally just, I mean, it's like a, well, we'll talk about the dot product later, but once I show you like the easy way to multiply matrices, you'll see how to do this with this way. The other way is to do this. So let's call the resulting matrix C. A times B is C. So the first entry is C1, and then we have C1 P, CM1, and then CMP. Okay. The second way is then where each of these CIs, each of these entry C's, C, I, J. Well, what is the IJ entry of this thing? Where for, I guess, a fixed I and J. Well, this is how we define it. We sum over uh, each. Let's see, so K E K J, which is just simply like A I1 B1J plus blah 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 to AIN uh, B and J. Okay. So these two ways, you can find it either using this way right here or doing this right here. These two ways is how we can define matrix multiplication. Now there are shortcuts to it. It isn't. I'm not gonna make you use that some disgusting sum that's there. I'll show you basically how to do it without having to worry about that. Okay. So, but first, let me remark: when does a matrix multiplication exist? So notice that these two matrices come from different I guess, sets of matrices, right? One has an n by n dimension, the other has an n by p dimension. So basically, if so, uh, so let's say, so remark. Um, so that, again, so let's say n was an m by n, and b was a n by p, right? So exists. Uh, so this only exists if so a times b. So if you draw the dimensions down here, you have to make sure that these inner ones match up. Okay, if those match up, then you're allowed to multiply. If they don't match up, then you can't multiply. All right. So these must match up. Okay. So let me shrink this down. All right, let's do an example in matrix multiplication now. So example 2.12. So uh, yeah, find AB where A is equal to 2, 3, 1 minus 5. B is equal to 4, 3, 6. 1 minus 2, 3. Okay. So solution. So A times B. First of all, is this product defined? Is it allowed? Yes, it is, right? Because this guy right here is a 2 by 2, and this guy right here is a 2 by 3. The inner ones match up, right? These two. Yeah, no, yeah, it doesn't matter. The inner ones are the ones that need to match up. Yeah. So the outer ones can be like different numbers if they want to be. They don't. But here's the other part. The resulting matrix will have dimension 2 by 3. Right? So this would be dimension of resulting matrix. Okay? So the inner ones must match up, and the outer ones is what the matrix dimension that it outputs would be. So okay, so yeah, so we're allowed to. So let's do it. So oops. So 2, 3, 1 minus 5, 4, 3, 6, 1 minus 2, 3. All right. So instead of doing the whole, that formal definition of multiplying matrices with that gross sum, and also even with the column vector stuff, this is what I do. Is basically, so let me shrink this down. So take this first row, and we dot product with this row. But what that just means is, so take that 2, multiply by that 4, and then add it to that 3 times that 1, right? So the first entry will be 2 times 4 plus 3 times 1. That's be the first entry. All right. So what is this? That'd be 8 plus 3, which is 11, right? Yeah. So yeah, so maybe I should just leave it there. So this thing will be 11. So that's the first entry. Okay, what about the second entry? Well, do the same thing, but for the second row. So now do it for, let's say, this second row right here. So it'll be 2 times 3, and then 3 times negative 2. So it'll be plus, that would just be 6, 3 times, well, 3 times 2. And that orange one becomes, what is that? So it'll be 0, right? Okay, perfect. Now do the same thing for this third one. So that third entry will also be 2 times 6, so 2 times 6 plus 3 times 3. So that results is to 21. Okay, so now you're done with the first row on A. Then you move on to the second row and repeat the process for the blue column, orange column, and green column. Okay. So again, so that'd be 1 times 5 minus 5 times come on, be 1 times 4. 1 times 4 minus, yeah. So that should be, I think it should be minus 1. Then do the orange one. So it'd be 1 times 3. So minus 5 times minus 2 is plus 10, so it'd be just plus times 2, like this. So this becomes 13. And then last but not least, the 1 times 6, and then the minus 5 times 3. And this results to minus 9. Okay. So this is, this is the quote-unquote shortcut, but it's just the result from the definition. But yeah, so whenever you multiply matrices, you do it this way. You do, like, I usually just go like this, if I forget how. But yeah, but later on, we'll learn the dot product. You can also just say it in terms of the dot product. So you can say the row vector 2, 3 dot product, the column vector 4, 1, and that's basically the first entry, and so on and so forth. But yeah, this is how you multiply. So at the end, you get precise. So at the end, all of this equals 11, 0, 21, minus 1, 13, and minus 9. Okay. So by the way, so what did I say that dimension of the resulting matrix would be? I said it would be a 2 by 3. Is this a by 2, 2 by 3? Yes. Okay. So you can check yourself if you did it right if the outer ones are what the dimensions of this matrix is. So yeah, so this is perfect. Yes. Okay. Yes. So let's move on to the next one. So now let's test more conceptual thing. So let's say perfect. So let A be a M 3 by 5 and B be a 5 by 2. What sizes are A times B and B times A? So according to this, what is the size of A times B going to be? According to what I just said, like previously.
3 by 2.
So if it helps, just do the thing, right? This would be a 3 by 5, and this would be a 5 by 2. So what size would this be? A 3 by what? 3 by 2. Yeah. So this would be a 3 by 2 exactly. What about B times A? Yeah, I can heard it. Yeah, it doesn't exist. Yeah. So yeah, if you write it again, 5 by 2, 3 by 5, you can see the inner ones don't match up, right? So this is not does not exist. This as a matrix does not exist. Yeah. So always remember when you're multiplying matrices, always check the dimensions of your matrices. You can't just you can't just multiply any matrix if you want. That's what's a little bit different with the structure of matrix operations. There's a lot less things you can do with matrices. Real numbers are nice because they form what you call field. Everything like goes. These things don't. So, all right. All right. So let's now connect all the stuff we've done to linear systems again. So, so recall from last chapter that we say we can represent a system of linear equations as a matrix equation, right? So you can do like AX times B. So now that you know how maybe you have a notion of what the matrix multiplication is, you can do this now, right? So if I give you a matrix equation, now the question becomes like if I guess you can say you can translate back to this, but if I give you this matrix equation, what am I solving for here? It's this equation, right? So the thing you're solving for here is the vector x. Okay. So now, like in normal equations, you would just say, oh, divide by 8, right? Well, we don't have a notion of division with matrices. We only have the notion of multiplication, addition, and scalar multiplication, right? So it's different with this one. So, but let's state a theorem that we can use to be able to translate the language of, let's say, solve ax equals b to something more familiar. So theorem. Let's say it's a 2.1.2. So let A be a m by n with columns. So this is the partitions, A1 all the way to AN. So if B is a, I don't think I did it. Okay, so hold on. Before I do this, let's, so first let's denote what Rn means, right? So what is Rn? So Rn you can think of as, well, there's lots of ways to think of it, but you can think of it all the set of all n-dimensional vectors where all these xi's come from R, right? So when we talk about Rn, this is the space of all n-dimensional vectors, okay? So let's say if B is a m-dimensional vector, right? Sorry. The matrix equation has the same solution as these two forms. So let's make this small. Come on, size. I have like 2 minutes left. So it has the same solutions as these two things. One, it has the same solution as this vector equation, which I'll say more about right here in a second. X1, A1 plus X2, A2 plus blah, blah, blah. Say X n A n equals B. Or the augmented, which is what we know, A1 all the way to AN, and then the equals, when we draw the line, this would be the line of B, like this. Okay, so asking you to solve a matrix equation amounts to asking you to solve either that vector equation or this augmented matrix. Okay, so okay, well then I think so next time we'll basically use this to solve some matrix equations. Okay, so I guess for right now, I guess yeah, a challenge question. Yeah.
Hello?
I know the perfect one for this one. So here so challenge. prove. So basically, I want you to prove this theorem right here. 2.12. So theorem. Oh man, I can't even spell. Oh, I can, never mind. Or maybe not, I don't know. So theorem 2.12. Yeah. So honestly, it shouldn't be very hard. It's actually pretty. Yeah, I'll send you the notes. No, don't worry. I'll send it through Remind. So all you have to do is write out the matrix equation, right? With the elements, or even just like with row vectors, and then use what we just learned with matrix multiplication, the definition, and also, yeah, I mean, I guess that even works. Yeah, so use basically this form. I would suggest you use this form right here. A combination of these two, and you'll be able to basically prove this theorem right here. Basically, so again, what's the theorem asking you? If you have the matrix equation, AX equals B, make it look like these two, all right? That's basically all I'm asking you. So get that equation, that matrix equation, and make them look like those two somehow, okay? Can you work? Well, unfortunately, I'll work on a homework problem next time. I can't do it right now because there's another class coming in, and I can't always just, I can't keep them from their class. But which one did you want me to work? I can note it down for next time. 10 from which week? Okay, yeah, I can do that. Oops. Do you have Remind? Send me a message with that, and that way I can remind myself of it. Okay, any other questions, comments, concerns? I'll send you this stuff actually right now. Export all.
I have a question.
Yeah, yes?
For the discussion, when do we need access to the discussion board?
Access to what?
So backpack.
Like a pack? You should have gotten an email, and also the email there should be an email with basically all that, with the pack link and all that. I also sent an email out with a key and the actual link. So use that key to find the class and then register through there. If you have any problems, just email me or request a Zoom meeting or whatever. And
okay, I sent you an email.
Oh, you did? Oh, like yesterday?
I think so.
What's your name?
Kyle.
Kyle. Okay, I'll look for it. Just send me another one. I am very forget. That's why I prefer Remind, because I always forget. But just send me another email, and I'll look for it right now too as well. But send me another one now, and I'll help you out. Okay.
Okay. Thank you.
Yeah. Yeah. So here. Oops. No problem. Leave.